Hi, folks. Today we're going to talk about algebraic functions, kind of. And so before we get into the algebraic functions, let's talk about the algebraic functions which we're going to talk about and how we got there. And so to begin with, let's start with pre-algebra. In pre-algebra, we bridge the gap from arithmetic to algebra. And so we introduce negative numbers and irrational numbers, building the real numbers. We introduce variables and combinations of variables, thinking of them as algebraic expressions. We introduce equations and the properties of equality. We then introduce graphing, but with a focus on introducing points and lines. We don't go too far in depth. We're mostly just introducing folks to the idea of graphing. All of this is in the language of binary operations. And so we use the properties of equality and that real numbers form a field to explore expressions and equations. We use analytic geometry to explore the algebra of various geometric objects, such as lines. But mostly in pre-algebra, it is just introductory stuff. We are just saying, okay, let's see if we can plot a point. Maybe let's play with a line, maybe a few other things, but not much more. In elementary algebra, we build on the pre-algebra ideas, but it's still in the language of expressions and equations. And so usually we extend expressions and equations to include more complicated polynomials, radicals, and rational expressions. We do a deep dive into lines and parabolas, learning about slope, how do you factor polynomials, and the quadratic formula. At this point, we are still focused on the idea of binary operations. And so polynomials are just combinations of the binary operations of addition, subtraction, multiplication, and exponents. Lines, quadratics, rational expressions, and radicals are still just combinations of basic binary operations. There's nothing really new yet. In intermediate algebra, we transition from the idea of binary operations to the idea of functions. While subtle, this is huge, and it's something which is often not focused on. A lot of folks feel that intermediate algebra is really just repeating the majority of the material from elementary algebra. But in transitioning to functions, that's a very large change. And so a function is a transformation from one set of real numbers to another set of real numbers. From a geometry perspective, we take one curve and map it to a new curve. That's a big deal. All of the structures from set theory, topology, and modern algebra are now in play. We don't talk about them because it's intermediate algebra, but it's all set theory, topology, and modern algebra. The functions of algebra are ultimately still based on binary operations, though. So we have linear, quadratic, polynomial, or rational, and radical, and then we introduce exponential and logarithmic. We also introduced the algebraic geometry of conic sections, which is what we get when we slice a cone and get parabolas, circles, ellipses, and hyperbolas. One thing which is kind of tragic is we don't really emphasize enough how all of these things come from a cone. We call them conic sections, and we introduce them because they're a fun little thing, which is a relation and not a function in general. But we don't really go in depth as to why we're slicing cones to begin with, or why we might want to slice other things. What does it even mean to slice something? That's a big part of what algebraic geometry used to be. And that's not something we focus on much these days. And so before we get into the details of all of the algebraic functions, we should do an important note. And so there are algebraic functions and there are algebraic functions, and there is a difference. Algebraic numbers are solutions to polynomial equations. And so we learned about those early on. There's algebraic numbers and there's transcendental numbers. And so the square root of 2 is considered an algebraic number because it's a solution for x squared minus 2 equals 0. And so square root of 2, definitely an algebraic number. Well, we have a similar definition for algebraic functions. Really, all of the rules, all of the properties that we have for numbers, we can apply them to functions as well. And in particular, we like to focus on the idea of polynomial functions. And so if a function can be written in terms of polynomials, we can often refer to it as an algebraic function. There's a lot more details to it, but we're not going to get into the weeds on that. For our purposes, and really strictly for our purposes, we're going to be focusing on functions of algebra when we're talking about our algebraic functions. And so we're thinking about the functions which you would see in an Algebra 2 course, as well as relations you would see in an Algebra 2 course. Not all of the functions are technically algebraic functions. E to the x, for instance, is a transcendental function, which means it's not algebraic. So a function is called an algebraic function if it can be constructed using algebraic operations, such as addition, subtraction, multiplication, division, or taking roots on polynomials. We can't do that with e to the x. We would need an infinite number of terms, and that causes problems. And so for us, we're going to group e to the x in with all of our other algebraic functions because it's introduced in algebra. That said, let's talk about the functions of algebra. Here are the functions you should already know from intermediate algebra. Intermediate algebra should be a prerequisite for this lecture series. And so hopefully you've already seen all of these. And we'll start with a linear function. And so a linear function is a function which has a graph, which is a line. We know lines. We've learned about them in geometry and whatnot. General formulas include point slope, slope intercept, and standard form. And here they are listed. As one of the more general structures, they pop up everywhere in the real world. Quadratic functions are formulas or functions of the form y equals a times x minus h squared plus k. If we wanted to, we could rotate it, and then it might not be a function anymore, but we can still play with it like that. In Algebra 1, we focus a lot on factoring these expressions, which is useful to find the zeros of these functions. While there are many applications, one of the simplest is gravity. If you throw something up, it will come down, and it will follow a parabolic trajectory. You do have to be careful. Wind resistance is a thing. It will mess with that. Yeah, but if you are dealing with something which does not have any form of air resistance, it'll just go in a parabolic trajectory. Parabolas are also conic sections. And so when we think about conic sections, we always have to remember quadratics are one of them. Next up, we have the cubic functions. And so a cubic function is a polynomial which has a highest degree of 3. And so it's going to have something which looks like this. An x cubed term, maybe an x squared, maybe an x, maybe a number. They usually look something like this, and we can get into how we can describe them a little bit more if you take a college algebra or pre-calculus course. But for our purposes, generally, they can have at most 2 humps, or a peak and a valley. The most common application of cubic functions is modeling 3-dimensional objects. And so if you're dealing with something in 3 dimensions, well, you can multiply those 3 dimensions together to find yourself some volume. Polynomial functions. And so polynomial functions are any function which is the finite sum of monomial terms, ax to the n. And so the degree of the polynomial is the largest exponent in the polynomial, and these things can get a little wild. We can see here we go up and down and up and down and up. We can try and determine the degree of a polynomial based on the graph, but really we can only approximate it, and we might be way off. There are other techniques to play with polynomials, in particular in calculus. But for us, we'll just think about where we can use them, and we can use them to model things which are a little bit more complicated. Polynomials tend to be fairly easy from a calculus perspective. And so if we're dealing with something which is messy, we can always just turn it into polynomials, and then it becomes something nice and easy to play with. Next one is the reciprocal function. And so the reciprocal function is the simplest rational function given by the formula f of x is equal to 1 over x. This is technically a hyperbola, which would make it a conic section. We don't often think of it in those terms, though, but it is. It has a horizontal asymptote and a vertical asymptote. Usually we don't use this function alone, but instead use it as part of a larger function. I mean, this is a simple ratio. And so if we are dealing with something where a ratio is involved, we might be using a reciprocal function. A rational function is a function which is the quotient of two polynomials. And so if we have p of x over q of x, where they are both polynomials, that makes it a rational function. And here's what a graph of a rational function looks like. You might have asymptotes, you might not. You might have vertical asymptotes or horizontal asymptotes. You might have oblique asymptotes, which would be where it's approaching some line. It may cross the x-axis, it might not. It might cross the y-axis, it might not. These things can look very different depending on what the polynomials are. Rational functions are used to model a number of physical things, including energy or movement. And one example is, consider the formula distance equals rate times time. If you solve for rate or you solve for time, you're going to be getting a rational function. Absolute value function. Oh, this is a good one. I don't know if I'd consider this an algebraic one or not. It might be a miscellaneous function. But the idea with the absolute value function is it's just the distance a number is from zero. That's how it's formally defined. But we can graph that. And so when we graph that, we end up getting something which looks like a V. So we have this point down here that it all approaches and then it goes back up. This is a translated version. We've shifted it back 2 and down 3. And so this would be f of x is equal to the absolute value of, let's see, how about x plus 2 and then minus 3 at the end? Yeah. Note that the absolute value of x can also be written as the square root of x squared. When creating models, we use this to force variables or expressions to be positive. We don't want to have any negative models, and so we make sure that they're all positive. Speaking of things that are positive, our square root function. And so f of x is equal to square root of x represents the inverse operation of squaring. Technically, this is the principal square root. And so the principal square root is the positive version of the square root. There is a negative version as well. And if we're thinking of the formal inverse of x squared, well, the inverse of x squared would not be a function because x squared is not 1-to-1. And so this right here is the forced version of it to be a function where we're just taking the positive version. And that's the principal square root. And so when we're saying the square root of 9, we're really saying the principal square root of 9 would be 3. We often use the square root to solve equations involving quadratic functions. Radical functions, they can look fairly radical. And so a radical function is something of the form nth root of x to the m, which we can also write in exponent notation as x to the m over n. These can look like a lot of different things. It really depends on the ratio of m to n. Radicals are frequently used as the inverses of polynomials to solve polynomial equations. There are a number of other applications of them, though, but that's one of the big ones. Exponential functions. So exponential functions are functions of the form f of x equals a to the x, where a is some number, some real number. In this case here, this is going to be 2 to the x. And you can tell that because at 1, we're getting 2. At 2, we're getting 4. And so this would be 2 to the 1 and then 2 to the 2. A popular and important base is e, which, as you might suspect, is named for Euler, as everything else is. E is an irrational number, and it's roughly equal to 2.718281828459045. I don't know pi that far, but I know E that far, mostly because I just memorized it. There's a trick to remembering this one. There's 2 things you need to know about Andrew Jackson. He was our 7th president, and he started office in 1828. That's right, 1828. And on a completely unrelated note, the angles of an isosceles right triangle are 45, 90, 45. That gets you like 15 spots with the number E. So 2 things to know about Andrew Jackson. 7th president, 1828. That's right, 1828. And then an isosceles right triangle is 45, 90, 45. Usually I don't recommend memorizing things like that, but for the number E, oh, it's fun. Exponential functions are one of the most critical in understanding the world around us, as they model exponential growth and decay. If we want to figure out how populations work, if we want to figure out how cells work, if we want to understand human biology, ecology, anything which is growing in a way which is proportional to its population, that's exponential growth. And so there are a great many things which are modeled using exponential functions. Logarithmic functions are the inverse of exponential functions. And so the whole reason we needed inverse functions was so that we could solve exponential functions. And logarithmic functions are the way we do that. And so if we have x equals b to the y, we can rewrite this as y equals log base b of x. These two things mean the exact same thing. And so really, this is just taking an exponential function and then just switching the x and y value. And note for this one, this is going to be the inverse of 2 to the x. And so this would be a log base 2 of x. And if you look, we can see at 1 in the y direction, we have a 2. At 2 in the y direction, we have a 4. And so again, this would be x equals 2 to the y, or y equals log base 2 of x. There are a lot of weird properties for logarithms and exponents, and so they might take some practice to get used to. Logarithms are typically used to model really, really slow things or to solve equations involving exponential terms. If you want something which is a function which goes incredibly slow, you'll usually just make it a logarithm or a logarithm of a logarithm. Natural log of x is one of the slowest functions out there. Now let's talk about some relations. And so conic sections. Our first one is a circle. And so a circle is a geometric shape. We all know what a circle is. It's the round one. It can be modeled by the equation x minus h squared plus y minus k squared equals r squared, where r is our radius and h and k are telling us the x and y values at the center. This is a conic section, meaning if you had a cone and you sliced it a certain way, you would get a circle. It is a simple geometric structure. We find applications of circles in lots of places. Again, it's the round one. And so hopefully we all know what a circle is. Semicircle, that is a half circle. And so the semicircle function is a function made from half of a circle. It is given by the formula f of x is equal to the square root of r squared minus x squared. Essentially, you're just solving for y in our circle formula. Circles pop up a lot in math, but circles are not functions. And so when we need to treat a circle like a function, we usually use the semicircle function. Next up, we have ellipses. And so an ellipse is a stretched circle. It is also a conic section. So if you slice a cone in the right way, you are going to get an ellipse. We have a formula for it. X squared over a squared plus y squared over b squared equals 1. It's a fun algebra trick to try and figure out where that formula comes from. How is this formula connected to the idea? Ooh, I went forward. How is the idea of this formula connected to a cone? And you can actually figure that out by solving equations. Ellipses pop up a lot in physics. There are many objects which we would expect to have circular rotations, but because of outside forces, they actually have elliptical rotations. The motions of the planets are elliptical orbits, give or take. Next up, we have a hyperbola. And so hyperbolas are also conic sections. If you cut a cone in just the right way, you are going to get hyperbolas. Hyperbolas do have some applications related to physics and lenses, but we don't play with them too much in general. Yeah, sorry. If you're a hyperbola fan out there, then yeah, enjoy it. Next up, we have some more miscellaneous functions. One of the big ones is the floor function. And so the floor function is a function which always rounds down to the next lowest integer. And so if you are anywhere between 0 and 1, it always rounds down to 0. If you are somewhere between 1 and 2, it always rounds down to 1. If you're between 2 and 3, it always rounds down to 2. And so this is a function which just always rounds down. If you want rounding to be in a more precise way, we can use the floor function. And we use it a lot in computer science. Do you want to round when you're 50% between two numbers, or do you just always want to round down? Well, often we just want to round all the way down. The ceiling function works the same way as the floor function, but now instead of rounding down, it always rounds up. And so anything between 0 and 1, it rounds up to 1. Anything between 1 and 2, it rounds up to 2. Both the floor function and the ceiling function are considered stair-step functions because of what their graph looks like. We generally use the floor function more than the ceiling function, but sometimes there's a good application for the ceiling function, and we can just go straight there. Final thoughts. Whew. So intermediate algebra introduces and goes in depth into these functions. How can we play with their structures? What are their properties? And how do we deal with equations? From an analytic geometry perspective, we are more interested in understanding how their graphs work. Now I've got this graph here, which got me into trouble a decade or two ago. I went viral for creating a graph of the Batman symbol using just our algebraic functions. And so this is just an algebraic expression for that graph, and went viral for it. Pro tip, don't go viral. It ain't worth it. With that, I'll let you get to work exploring where you find analytic geometry in the real world. Good luck, folks.